Right. So your voltage drop, it's basically your Ohm's law formula for voltage. So E is just equal to I times R. For your percentage voltage drop, your percent VD, it's going to be equal to EVD, which is basically your voltage drop. VD is voltage drop. And then you want to divide that by your source voltage, multiply that by 100. For the NEC, I'm pretty sure we got told this I think it was our first semester. Like the maximum percentage of a voltage drop at the farthest outlet in a circuit wasn't supposed to go any lower than 3%. That was like the recommended amount in the NEC. Let's see. Or a couple other formulas. Right, so you may end up with a couple of questions. Actually, you will end up with a couple of questions for lesson 4 where they don't exactly, give you your amperage and resistance in any kind of a straightforward manner. So there is one other formula that you can use to calculate your voltage drop. And that is your constant K multiplied by your amperage multiplied by the length of your wire, specifically in feet, multiplied by 2, and you divide that by the cross-sectional area of your wire measured in circular mils. There's at least one problem on the homework assignment where you'll have to use this, and if you specifically just need to get the gauge of your wire, you can literally just flip your voltage drop and your area circular mils around. So AC mil would be equal to your constant K times your amperage times your length in feet times 2 divided by your voltage drop.
See, I won't lie, that's where I got stumped on one of the questions. I was like, I forgot how to figure out the wire gauge.
Yeah, that's
So that makes
I
that helps a lot right there with a couple questions.
I know there's a table. I think I don't know if it was on one of our papers or
There
somewhere in the code book. There's some table we could use to do a conversion for circular mills and American wire gauge. I just couldn't find it. But yeah, for that one, I honestly just gave it a like really rough guess.
Yeah, I've been flipping all through the the code book, so I can't. I want to say it's. I thought it was like chapter 9 or chapter 9, table 8 or something like that.
Let me take one more quick look through here.
Let's see.
Just look at my tabs
I
here.
think it's 689 of the code book. I think it's chapter 9, table 8, conductor properties.
Oh, maybe that's why I couldn't find it. I didn't actually try looking back there.
So I got everything labeled.
Okay. Oh, I think this is it here. Because one circular mill that was
Forgive my cat. She's in slut mode.
oh. Check something real quick here. I think I found the table for it. Actually, wait. No, never mind. No, that's not.
Well, I pulled out notes from DC Theory because we went over all a lot of this is like a it's kind of like a refresher of these,
Yeah.
all the voltage drops, the resistivity for copper and aluminum, and how to convert from how to convert square mills to circular mills. So.
Let's see. Right. So the next part. You may have gotten to this problem already, but there's going to be at least one problem where you won't be given the source voltage. That'll end up being your unknown. And they'll basically give you some resistances on your wire, and you'll also have a load, and they're just going to give you the rated voltage and the rated power.
Yeah,
And
I think it's.
And
I think it's 13 through 21 or 22.
Oh yeah, starting at 13, that goes through. Honestly, that goes from that's like starting at 13. There's just one problem that just runs on for like half the assignment. But right before that, though, you're gonna end up. Was it 13? Yeah, no, 13. You're gonna get the source voltage, but for number 12 specifically, that's the one where you're not gonna get your source voltage, and you'll need to figure it out. And effectively, what you're gonna have to do is they're going to give you the voltage you need at the load. So what you basically just need to do is calculate your voltage drop, and then effectively just add that to the rated voltage, and that will be your source voltage. So basically, EVD is equal to IT, basically your total current multiplied by your resistance across that particular path. So I guess I might as well just do this one here. So
let me figure out how to switch over the video. I don't know how to do that.
Oh, to like a webcam?
Yeah.
Should be.
Do I have to add you as a friend?
No, you shouldn't have to. Go to. So right in the Discord window, if you look right down below where both of our names are in the voice channel, there's two buttons. There's one for video and one for screen.
Yeah.
Just click on the video button, and that'll turn on your camera. Ooh, that didn't work. Looks like that didn't work. Anyway, do you want me to do an example for this one, or should I just jump ahead up to 13?
Well, I mean, so far I've only gotten to 13, but like, I mean, everything else I felt confident on. I expected, like, I was just gonna listen,
Okay.
you know, because I haven't gotten that far into the quiz to where I have questions. Like, really, the main thing was, you know, because I got the formula for, let's see, I got the formula for, you know, voltage drop, the different formulas that you can use, and for the percentage. And I was struggling with which formula it was or how to calculate wire size that you would need.
Okay,
And so you
yeah.
kind of answered that question. So,
Yeah, that's
but
what I've been having trouble with too.
yeah, I was just gonna listen because I started one of the videos. I mean, everything else has been kind of easy, but I mean, like, one, you know, yeah, it's really just, you know, I haven't had as much difficulty probably as other guys in our class, but
Mhm.
I just wanted to listen
Okay.
because I knew 5 was short, and Friday I started 4, but I was just so mentally worn out Friday that I just like drew a blank on everything. So I was like, okay, I give up. And then I work Saturday. I work Saturdays and Sundays. I usually work 7 days a week, so
Hmm.
I just try and do it myself. And then if I have questions, I ask somebody. But most of the time, like, it's all in the notes. So,
Right. So right. So the formula for this. So to get the current, we're gonna use the. So it tells us we've got a motor with 5 horsepower and 240 volts. So we can use the right. So you recall P was equal to I times E, right? Power
yeah.
equal to amperage times voltage. So we can just do a simple rewrite of that because we're looking for our current. So we can just do I is equal to P over E, and it's 5 horsepower. So you do the math really quick. The conversion into watts. It's gonna be 5 times 746. Yeah, 3730. So it's gonna be 3,730 divided by, and the voltage we want to get for this is 240. So we do the math there, and it's going to be 15.541, and then just repeating 6 in amps. So we've got that. The resistance, the calculation for that is really straightforward. We literally just add the resistance of all of the wire. So in this case, it's just 0.75 plus 0.75.
1.5.
Yeah, because we got 0.75 on each side of it. So EVD is going to be equal to this amperage that we just got here, 15.5416 times our resistance, which is 1.5. And that's going to come out to about 23.3125 volts. So that's our drop. And we know we want 240, so we literally just add 240 to that, and our answer. I don't know why that looks backwards on my camera. That does look forward to you, right? On your view.
I couldn't get the video to see, so it's okay. I'm
Oh, okay.
listening.
But yeah, you should end up, once you add this voltage drop to your desired voltage at the, at the load, you should end up with about 263 volts. Right, but yeah, for number For number 13, that problem extends all the way up through, let me see. So 13 through 28 is all that same exact diagram. So kind of important that you don't screw up. I don't know if we're gonna have something like this on the test. Hopefully not, because I mean, you screw up on one calculation, you're probably gonna screw up everything else too.
Yeah.
And I'll go ahead and I'm just gonna draw this here for everybody else who's watching the video later. And I'll do just one part of this, and then everybody should just be able to figure out all of the other parts of it, because it's the same process for the whole thing, more or less.
It's
So,
pretty much just doing a partial, right?
doing what?
Or a combination circuit. It's pretty much doing a combination circuit.
It's just like doing a combination circuit, yeah, with just a few extra steps. All right, so we've got our generator G right there. Symbol is going to be E with a little sub G. It's outputting 120 volts. And that generator, the wire running across, has a resistance of 0.22 ohms. And then it's going to split off into several loads. So we've got a motor. I've got 3 separate lights. And let's see, the motor is, now this is the rated voltage for the motor. It's 120 volts and 0.5 horsepower. And then each of the 3 lamps, they're not getting 120 volts, but they're all rated for that amount. 2 of those lamps are rated at 100 watts. And then the one at the very end is rated at 75 watts. And all of these loads are all completely in parallel with one another, but they're also in series with the wires running to and from your power source.
Yeah.
And we've got resistance RB for the other wire, and that's also 0.22 ohms. So effectively, all of the questions are just going to require you to, you're effectively going to ERP this. So I'll ERP just one of these, and you should be able to do the rest just fine. So I'll do the ERPing for this last light at the far end that's got 120 volts and 75 watts for the rating. So we've got our E, I, R, and P. So 120 volts is our rated voltage, but it's not the actual, so we don't have E. We don't have high. Or at least we have the rated voltage. And we've also got the rated power. So there is a little thing that we can do, because the resistance isn't going to change. So we can basically use the rated voltage and wattage and just use Ohm's law to calculate the resistance right there, right off the bat. And let me double check and see what that equation even was again. Okay, so the equation you can use to get the resistance of your load is going to be the voltage squared divided by the power. So assuming this was getting 120 volts and consuming 75 watts. You could take that 120 volts, square it, divided by your 75 watts of power, and you can calculate and figure out that that load, that light, has 192 ohms of resistance. And, oh, you know what? I just realized I do need to calculate the resistances of the others to do the rest of this. So basically what you're going to do is you're going to do that same thing to figure out the resistance of the other two lights, figure out the resistance of your motor, and then from there what you can do... Did somebody jump in? I think somebody jumped in.
Yes.
Oh, cool, you're here.
Yeah, sorry for the delay.
Okay. So we're just going over number 13. I'm just doing a little bit of it just to show how it's solved, basically. Right. You able to see the feed okay?
Yeah, I can see it.
Okay, cool. So you're going to end up with this one problem, and this is going to take up like half the quiz of this assignment, is you're going to have this circuit here. So you've got a generator, and it's outputting 120 volts of power. You've got your wire running out to your loads, and the wire has a resistance of 0.22 ohms. And then you've got 4 different loads. You've got a motor, and you've got 3 lights. They're all in parallel, and they're all rated for 120 volts. And the motor's rated for 0.5 horsepower in terms of power. 2 of the lights are rated at 100 watts, and then another one at 75 watts. And those are just the rated amounts, but not the actual. It's not the actual voltage or power that they're getting. And that's part of what you're going to have to calculate. And then you've also got down here is the rest of the wire, and that's got a resistance of 0.22 ohms. So when you've got a load like this, and you're trying to figure out what the actual voltage, current, or resistance is, you can figure out the resistance right off the bat by using the formula, which is your resistance being equal to your voltage squared divided by your wattage, which is these rated values here. Because regardless of whether you're giving this load 120 volts or any other voltage, the resistance is only going to be the same. So you can literally just take this. So for instance, this light here, you can take 120 squared divided by 75, and you'll know that your resistance for that particular light is 192 ohms. And then you can repeat this for the other sources too. So I'll just go ahead and ERP those other ones really quick. I'm just going to do part of this, and then like the rest of it should be really straightforward to figure out. Okay, so this one, it's going to be 120 squared divided by 100. So it's going to be 144 ohms for that one. This one's got the same rated voltage and wattage, so same thing. That one's in horsepower, so you'd have to convert it. 1 horsepower was...
It's like 700 and something watts, I think.
Let me
I can
double
look
check.
it up if you need me to. I got it wrote down.
1 horsepower is... I've also got to note it down here. I just got to find it.
Hold on. My notebook's down yonder. So I remember seeing this question when I went over it. And I was like, I wrote that down.
I think it should be 746.
Sounds right.
Yeah, it's 746. So half a horsepower. So that's going to be 373 watts. I'll just write that down there. Okay, so then we can figure out the resistance of that. So it's going to be 120 squared divided by 373. So that motor is going to have a resistance . 38.60 589.812 ohms. So once you've got the resistances of all of these, you can, since they're all in parallel, you can figure out what their collective resistance is. So figure that out there really quick. So basically all of these to the power of -1 added together and then put back to the power of -1 again. Okay, so you should get for this whole thing, just using the formulas that we learned in DC theory, that the resistance of this whole section here is going to be 22 point, just repeating 2 ohms. And then if you add these two here, your resistances of your lines on both sides, you can figure out your total resistance, which is going to be so it's going to be 22.6622 ohms. So at that point, you've got your source voltage, you've got your total resistance, and from there,
you just should be able to ERP it, right?
sort of. So what you need to do is you do need to figure out what the actual voltage is here, because we're for lesson 4 it goes into voltage drops. So even though all of these loads are rated for 120 volts and your generator's outputting 120 volts, that's not the voltage that's actually reaching to these loads. You've got a drop because there's some resistance in your wire. And your formula for your voltage drop, there's 2 formulas specifically. The more complicated one, if you don't have your resistance of your wire given, your complicated formula is right here, where your voltage drop is going to be equal to constant K multiplied by your current multiplied by the length of the wire in feet times 2 divided by the cross-sectional area of your wire in circular mils. That's the more complicated one right there.
Yeah, where you need your code book to look up the C mills and crap of the wire you're using.
Yeah. Now, your more simplified one is right here, which is your voltage drop, your EVD, is going to be equal to your current multiplied by your resistance.
Total current and total resistance?
Yeah, total current. Yeah, total current and your total resistance effectively for this specific problem here. And we've got our voltage right there, 120 volts. We've got our resistance now. So what we can do is take our voltage, divide it by our resistance, we'll get our current. Actually, wait, sorry. Did I get something wrong here? I feel like I'm forgetting something here. Give me a second here. Okay, no, we do have this right. Yeah, so yeah, your basic formula of E is equal to I times R. Basically, you've got your voltage here, you've got your resistance. So you use that to figure out your current. So 120 divided by 22.66, repeating 2. So your amperage is going to be 5.295. You could just rewrite it as 5.3 amps. So we know we've got our amperage, we've got our resistance. So from there, let me make sure I'm looking at this right too. Right. So what you basically need to do is once you've got your resistance and you've got your current, actually no, for this part you just need the current. So your voltage drop between your source and your load, the formula for that, it's going to be your amperage multiplied by just the resistance, the total resistance of just the wire. It's effectively the same of, you know, just like getting your voltage drop for anything, you know, in a series circuit. So we're just looking for the voltage drop across just the wires. And that's on both ends.
So do you add those two together?
Yeah, so you'd add these two together. You'd want to add the resistance of all the wire that's running between your source and your load. So in this case, we've got 0.22 ohms here, 0.22 ohms here, so it's going to be 0.44 ohms. We'll multiply that by our current that's running through it, which is 5.3. So we know that across all of the wire that's running between our generator and these loads is going to come out to 2.332 volts for our drop. So it's a 2.332 volt drop. Now if it's dropping by that much, it's just simple math. Take 120, subtract your voltage drop. You've got the actual voltage being delivered to all of these loads. Since they're all in parallel, they're all going to get the same exact amount. So 120 minus 2.332. So that means you get 117.668 volts going to all of these. And once you figure out what your voltage is, you've already got your resistances too. So from there, you can just do some quick, simple math, you know, just your basic erping, and figure out what your amperage is and figure out what your power is being used at each of these individual loads. And that's what number 13 through like 27 or 28 is going to ask you to do.
So I have a question. It's probably dumb.
Mm-hmm.
Probably something that's been reviewed or whatever. But with regards to the voltage drop affecting the load, wouldn't that only include the wire going to the load and not necessarily also from the load?
If it were a DC circuit, yes, but we're dealing with AC circuits. So with an AC circuit, you need to take into account the wire both on the hot and the neutral side of your circuits.
That's right, because it balances between both.
Yeah.
Okay. Thank you, sir. Thank you, Teach.
And I am
our new second-year instructor here.
I'm pretty sure that's why there's that ×2 in this specific formula here, because it's accounting for both sides of the circuit, both the hot and neutral, if I'm understanding it right. So that's a pretty big chunk of the entire thing right there.
Are you also uploading this to YouTube?
Yeah, I'm going to upload it and post it today. And then possibly tomorrow I might do 5 and 6 together in one stream. I know 5 is going to be a real short one. I haven't delved into 6 just yet.
I haven't done 5 yet. I've been going back over all the other lessons to make sure I actually understand them for the test. Which apparently, from what I saw in our text messages, we won't be going over in class, so...
Okay, so there's one. Actually, there's only one other. Yeah, just one other problem I'll do a little bit of just to show you how it's like the method for solving it, and then the rest you guys should be able to do on your own. So I'm gonna have a similar. I shouldn't say similar. You've got circuit with a bunch of loads. This is the one that really threw me off. Okay, so you've got your power source here. It's at 120 volts. And you've got all of these different points of resistance. So you've got a resistor right here, so IR, and it's got a current of 3 amps. You've got this right here. Oh, actually, I'm sorry. That's a motor. So you've got a motor, and the current, so IM, current in the motor is going to be 1.5 amps. And this here is actually a light. My bad. And the current going through that light is 2.2 amps. And it's going to ask you to calculate the voltage drops and give the voltages. Or was it just the voltage drop? Yeah, you need to calculate the voltage drop across each of these loads. And the voltage drop is going to differ because you've got different amounts of resistance across these lengths of wire. So you've got 0.4 ohms across each of these two sections. You've got 0.2 ohms.
So, like the last problem, would you basically take those in steps and solve
Yeah, you
the
have to
first
you have to
little
do
block?
this in multiple steps.
Well, yeah.
And then you've got 0.1 ohms across each of these two. So once I do the first part, you should be able to figure out the rest of this pretty easily. So for the first one, you're going to use that same formula again, which is your voltage drop is equal to your current times your resistance.
Which the resistance would just be 0.8, right? If you're just taking that first section.
Yes.
How did you go to the second little load? Is it the third one? Sorry. Long day in the sun.
Let me just double check my calculations here really quick. Oh, right. Sorry. Okay, this was the part where I screwed up. So, what's your I for this instance? When we're calculating the voltage drop across this load
just
right
be
here.
3, right? Because that's what's going through that first load.
It's actually wrong. And this is where I screwed up last time. So now you've got that. Now it is correct. You've got 3 amps that's going down across here, but the total amperage
Oh, you have
that's
to add all
going
3 of them together.
throughout all of here, basically the amount of amperage that's entering into this node here is 3 amps, but there's also the additional 1.5 amps here and the 2.2 amps here that are entering into this node, and then that same amount exiting back out from this node here, going back to your power source. So, actually, let me just double check this now to make sure it's all right. Which is 5.3. Right, so for this first section, it's going to be your amperage going through this whole point, so it's going to be 3 plus 1.5 plus 2.2, which is going to be 6.7 for your amperage, multiplied by your resistance, which is 0.4 here and 0.4 here, so times 0.8. So your voltage drop is going to be 5.36. Your source is 120, so 120 minus 5.36 is going to be equal to,
Should be 114.64.
correct.
Ah.
So that's your voltage across this point here. Basically your voltage between here and here.
Yeah.
So the trick for figuring out the voltage drop and as a result the voltage across these other loads, you now know that the voltage between this point here and this point here is 114.64, right?
Yes. Sorry.
So what you could effectively do is you could just sort of look at this as if there were just a power source here now that was delivering 114.64 and be the same effect. So it's basically the same way as if you were looking at this source here, and you've got a potential voltage of 120 between here and here. You know you've got 114.64 between here and here. So for calculating the rest of this, you can just ignore this whole portion and pretend that there's just a power source right here. That's at this.
Oh, to change it out for the 114.64
Yeah, at this voltage, because you know that the voltage between here and here is this exact amount now. So you could literally just rewrite the whole circuit if you really needed to.
Wow, you got a lot of dynamo.
So it would be like looking at, it's effectively looking at the circuit like this. I'll just redraw it really quick here. .2 ohms.
No, I get it. You basically just cut the first 0.4 section
Yeah, you
off
just cut
and
this
treat
whole
that as
section
your
out,
source voltage.
put that in there, and you know it's 114.64, and you just rinse and repeat the whole calculation all over again.
And then when you get to the last one, I assume you subtract that from your original 120 volts to get your overall voltage drop.
Across
Assuming that was the question. Yeah, across the whole thing. I don't know what the actual original question was, but
well, the only thing that you have to do is for the homework assignment is you need to figure out your voltage drop across. You need to figure out the voltage here across this load, the voltage across this load, and the voltage across this load here.
Gotcha.
That's all you got to do. If you wanted to figure out the voltage drop across the entire thing, I'm not sure if you could use the same. I'm not sure if you could use that same equation for this one if you wanted to figure out the voltage drop across the whole thing. Because in that 13 through 28, the wire. You had just the wire in series with all the loads, but you've got, this is like a series parallel kind of mix here. So I'm really not sure, but yeah, you don't really need to figure that out for any of the homework assignments so far. And yeah, that's actually everything to cover for this one, unless you've got some questions.
No, sir, I do not.
Okay. All right. I guess we'll go ahead and end the stream here then.
Well, thank you, sir. I appreciate it.
Any questions, Bree?
No, I'm good. Thank you.
Okay, cool.
All right.
Later.